So it's an entirely automatic little cupboard light. It's got a 1 meter warm white LED strip, and you just tack it onto anywhere and it'll automatically turn on when you wave your hand in front of it. A very practical little device, and I like the idea. However, I've done some testing on this thing, and if we apply power to it without even turning it on, you'll see that it's drawing 3 milliamps just sitting around. And that means that you're going to be draining your batteries in about 2 weeks, even if you never ever light this thing up. And I think that's entirely unacceptable. You can't use this with non-rechargeable batteries, and even with rechargeable batteries you're going to be swapping batteries so often that you're going to run very short on patience very quickly. So I figured we'd try and remedy the issue. And here is the schematic for the entire device. It's very simple indeed. So the part of the circuit that is causing the high current draw issue is this voltage regulator right here, because the power supply, which is 6 volts derived from the 4 AAA batteries going into it, are just going through a 1K resistor into a 3 volt Zener diode, which is providing the regulated power supply to the AL412 PIR chip, which is providing the light sensing automatics. And this circuit is inherently very inefficient, since we've basically just got a voltage divider here. There has to be a current flowing through this resistor to ground in order to create this stable 3 volt rail. And to top it off, the current needs to be sufficiently high to always power this chip, no matter what, whether or not it's actually doing anything. And that's a very cheap, dirty way of doing it, which works excellent if you're running something off of the mains, but not off of a battery. So the way I've intended to remedy that is by just installing one of these. These are simple little linear low dropout 3.3 volt regulated chips, and these have a quiescent current of specified 68 microamps, which is many orders of magnitude better than these 3 milliamps we see with the current circuit. I have checked the datasheet for the AL412 PIR sensor, and this is specified for an idle power consumption of 65 microamps, so really the 3 milliamps we're seeing through this 1K resistor is entirely unjustified. So if we have a quick look at the rest of the circuit, there really isn't anything here which would cause the high idle power draw, and the rest of the circuit works just fine. So from the 6 volt power rail, we've got it going straight to the positive end of the 5 volt LED string, and it's going through a couple of switches which enables you to run the strip manually with the switches on the board there. There's very high impedances here, 10k, 100k class resistors, nothing's going to draw any current. The switching device is a little tiny SOT23 MOSFET, which isn't going to draw anything idly, and there's going to be no current flowing through the LEDs when it's powered off. So it is a rather nice circuit, all of this. I don't mind it at all, save for the power supply part. So with no further ado, let's replace this thing with something a bit more modern. Alright, and here you can see the board, and this is the power supply circuit we're interested in. We've obviously got the passive infrared sensor module there with its time setting resistor, but this is the power supply. So we've got the positive terminal of a battery coming in here, feeding through the 1K resistor, into capacitor, into the Zener diode, into another capacitor, and this plane here is our stabilized 3 volt rail. So what I'm planning on doing is taking my little 3 volt regulator. We've got the input on this pin here and the output there with ground in the middle. So I think I'm just going to tack that on right there and bridge over this resistor and take the Zener diode out of the equation, and really that should be about it. We also need to connect the ground point of the regulator to ground on the battery terminals, but that's a very quick wiring job indeed. So let's just get to it. we need to cut the middle leg of the regulator out so that we don't short anything to ground. There we go. It is gone. There we go. That should now work decently. We might have to add a bit of extra capacitance across the input of a regulator in case it's a bit gripey, but we'll have to give it a try first. And here's the moment of truth. Let's see if we've improved anything. And we definitely haven't. Something's not working. That's of course because I've been an absolute idiot in wiring this up. So if we have a look at the schematic and how I've connected this up, we can notice that I've connected the output of a regulator to the anode of a Zener diode. Now the anode of a Zener diode is going straight to ground. So what I've done here is I've just removed all the power regulation for the PIR sensor and installed a shorted out 3.3 volt regulator. Oh, what mistakes. So what I need to do is just to turn this around slightly so the output is actually going here rather than this point, which is ground. Whoops. And there we've got it done up correctly. So you can see I've now removed this resistor and bridge altogether, and we've got the battery input going to the input of the regulator, the ground going to ground of course, and the output of the regulator going to the output rail, which is indeed this track, not that track, because that would be ground. So now this should work quite well, and we should see a drastic improvement in the idle power consumption. Let's give it a go. Alright, so let's feed some power and see what happens. And that would be an idle power draw of 74 microamps, which is damn near an order of magnitude improvement over what we saw in the stock configuration. Indeed, this is 40 times lower than that, and rather than having to change your batteries once every 2 weeks, we're now looking at changing your batteries once every 4 years. So now we've actually moved on to territory where self-discharge is going to be your bigger concern, even if you're using the stock AAA batteries. And I think that is a good result. And here is our new and improved circuit. So, as you can see, we've removed the 1K resistor and the 3 volt Zener, removing the leakage path from the battery, and we've pretty much just put our LDO in there instead. We've got the extra ground reference going there, but beyond that we've just replaced this resistor with a referenced regulator. So in this case I've used a microchip MCP1755S-3302E regulator because that's just what I happen to have in stock. And in this case it means that beyond just improving the idle power draw, we've actually turned this from something which just runs off of 6 volts to something which can run off of pretty much 3 to 12 volts, because we no longer have the issue of this being a very crude regulator. If we were to push 12 volts into this in its original configuration, there would be so much current running through this 1K resistor that this Zener would probably burn and short out, or would get a way too high voltage across the AL412 PIR device and burn that. So this thing can pretty much switch any kind of load you want, and you could run this off of 1 lithium cell or 2 lithium cells or 3 lithium cells if you wanted, just to adjust the light strip accordingly. The original one is of course a 5 volt rated one, but I've tested it and it runs fine up to a 2 series lithium pack of 8-9 volts thereabout. No worries at all. In the original configuration this strip is running very cool indeed. I've done some rudimentary research on the switching MOSFET here for the LED strip, and it is labelled A2, and I haven't been able to find any properly good source for what it might be, but I would imagine it's a maybe 1 to 2 amp rated transistor at best. It is a MOSFET, that we can say for certain. So I think this is just fine for switching 12 volt loads up to, well, 500 milliamps going through this thing is probably not going to be a big deal at all. So really you could switch a rather beefy LED strip with this thing, if you wanted to. In my case, I'm just going to keep the original strip. I don't need anything much bigger, I prefer having a long battery runtime. So that's about it. Thank you for watching. As far as this Clas Ohlson product goes, it's really rather shoddy from the factory, but with this minor modifications, we've turned it into something rather good. The price of €12 in a brick-and-mortar store isn't all that bad, really, all things considered, but you can get these similar modules on eBay or AliExpress for a fraction of the price, and if you want to modify it anyway, you might as well do it, unless you have a specific use for this admittedly rather nice AAA battery case. In fact, I might recycle this case for something else. I like it. It's pretty stylish, very clean design. So I hope you liked this video. For more information, click the link in the description.